All right, hi. Time for part two of the working memory and cognitive control set of lectures. What I plan to do with this one is to just cover this particular experiment on the psychological refractory period, and then make a third video for the working memory stuff at the end. I'm trying to make these videos shorter, more digestible chunks as best as I can. And I think in this case, it really makes a lot of sense because it can be a little tricky to kind of wrap your head around the logic of this particular study and the results and what it means for theories of attention and control. So one of the things that we've mentioned several times in this whole set of notes about cognitive control is what happens in these dual task conditions or divided attention conditions, multitasking conditions. And so what we're seeing here is that in many cases, when you're trying to do two things at once, I have to have some degree of cognitive control where I allocate my attention and my resources to one task, and then I have to shift over to another task. And so one question we might ask is what's while I'm engaged in one task, I certainly have some knowledge and awareness of the fact that there's other tasks awaiting my attention. So we might ask questions such as, what am I doing about those tasks in the background, right? Is there any task processing happening in the background? Maybe you could think of this as something like what happens in a computer, right? So in a lot of modern computer processors, they talk about things like multi-thread processors, and they're able to do a lot of things in the background. So while you're doing some computationally intensive task on your computer, it can still be doing other stuff right behind the scenes. So now let's think about humans, right? So while we're engaged in some kind of task where we're doing something, how much is going on behind the scenes, right? What else can I really do? That's what this kind of experiment is trying to do. So it's really asking a simpler way of putting it here, in a dual task situation where I have to perform task one and task two, it makes sense to expect that these tasks will somehow interfere with each other and that performance on one will be delayed. But then the question becomes, why, right? What's happening that causes the second task to be delayed? Where is the specific interference happening in all of the many stages of cognitive processing? Where do we find the interference happening? So here is a breakdown in words of what's going on with the experiment. We have two tasks. We'll call them T1 and T2, right? T1 is you're going to hear a tone, a sound. It's going to be a low or high pitch. And you have to respond by pressing a button, one of two buttons, right? So if it's a high tone, you press one button. If it's a low tone, you press a different button. I'm going to go to the next slide, but I'm going to come back to this here. So only pay attention to the top half of this slide, all right? So what we're looking at is a map, maybe a flow chart really, of the stages of processing involved with task one. So S1 is our stimulus, as the triangle here. That's the tone, right? High or low pitch. So I have to engage in perceptual processing because this requires me to perceptually discriminate which stimulus was that. I have to decide, was that the high pitched tone or the low pitched tone? And then after I have engaged in that processing, I have to select a response because I have two possible responses here. Press button one or button two, and then I execute the response. And so our total reaction time can be mapped out here as the time from when stimulus one appears, the tone, and when the response execution is performed at the end. But we see that there are these stages of processing happening in between. Now let me come back to the previous slide. Task two is there's going to be a letter on a screen. So in addition to waiting for a tone that comes over headphones, you're also going to see, you're sitting at a computer screen where you see a letter. And so it may be A, B, or C, right? Three possible letters that you can see. And now you have a different box that has three buttons on it. So one box has two buttons, and that's for your tone response task. A different box has three buttons, and those are labeled A, B, C, so you have to press the appropriate ABC button to go with the letter that you see on the screen, right? That's all there is to that. But because we're doing this at the same time, but not literally at the same time. So the way this works is that there's something called an SOA, stimulus onset asynchrony, and that means the tone task one, always occurs first, and then we're going to wait some period of time before we show you the three letters. And so your task is to respond to the tone as fast as possible, but you are also supposed to respond to the letters as fast as possible. In a control condition, we're just going to have people perform the letter response task. And what we can imagine is that the reaction time to the letter response task 2 in the control condition is going to be a lot faster than it is when it's compared to when it's the secondary task that's happening at the same time as this tone task 1, right? And so this is what I have now. Let me come back here to this other diagram on this bottom half. So we see essentially the exact same series of cognitive processes, right? We have S2, that's the A, B, or C letters on screen. And then it's followed by perceptual processing because I have to discriminate and recognize which of those three letters was that. Then I have to select which of the three buttons that I'm going to press, and then I'm going to perform that response. But now we also see that there's an SOA on here as well. So that represents the little time delay between the timing of the tone as for task 1 and the timing of the letter in task 2. And that's why this whole diagram on the bottom is shifted a little to the right. We have implied that here that there's time on our kind of our implied x-axis in this graph, right? Time goes from left to right here. So the SOA is the time delay between the onset of T1 and T2, the stimulus part. So as I said, we would expect your reaction time to T2 will be long compared to when it's simply just performed by itself, which is our control condition. And now we want to know why. Let me come back to this diagram again so we could ask a few questions. One possibility might be is that because these stages of cognitive processing look similar, we might ask questions such as, does this mean that the interference happens at the level of perceptual processing, that I can't simultaneously process the auditory stimulus and the visual stimulus, so I have to wait and finish processing one before I can shift over to the other? Is it maybe at some other stage of processing, right? So that's what we want to try to figure out here. Maybe it's at the response selection phase where I can't really do those two things. And in fact, you might notice that that's kind of how I drew it here, that for the bottom task 2, I made the arrow connecting perceptual processing to response selection a little bit longer, and there's a longer gap there, as if maybe that's where the delay is, right? And that maybe what has to wait is not perceptual processing, but it's the response selection that has to wait. I drew it that way for a reason because I'm previewing and giving away what the data supports here. But what I also want to make sure that you understand is why does the data support this particular interpretation? Let me come back one more time to this previous slide. There's another variation that I didn't mention. What we're also going to do is manipulate the difficulty of task 2 by making those letters A, B, and C either easy to see or harder to see. So high intensity means a nice high contrast, A on, dark A on a white background kind of screen. A low contrast, low intensity would just be where it's maybe faded very heavily. So it's like a light pale gray A against a slightly less gray background, much harder to see. So we're increasing the perceptual workload in the low intensity version here, right? So let's come to our predictions and results here. So this idea that I just mentioned that the competition might be happening, the interference might be happening at the level of perception. This is actually consistent with some of the theories of attention that we mentioned in previous chapters about early selection filter models, right? So an early selection filter means that information is as it comes into our senses, then I'm going to only let things in that are part of the current task that I'm engaged in. And if it's not part of the current task that I'm engaged in, we're going to filter it out. We're going to block it, right? And it never comes in to any other stages of internal processing. So what this would then imply for the task that we have set up here is that once I hear the tone and I begin task one, then any letters that I'm seeing on screen are irrelevant to task one. And that means that I will not even begin to process them until after I'm totally done with task one, right? I'm just going to ignore that entirely. And so that would mean that I'm not going to process that stimulus, that letter, and do anything at all with it. I won't even bother paying attention to whether it was a letter A, B, or C until I'm completely done responding to task one. So what this would predict here is that if this theory was true, we would expect that you would have long reaction times to task two, and that it would not matter whether or not the SOA, that stimulus onset asynchrony, was very brief and task two begins shortly after task one, or even if it was long, because again, you're still going to have to wait until task one is complete before you even start on S2. So it doesn't matter. Let me run back to this picture. Here, it doesn't matter whether S2 is presented in the early stages of S1, where the perceptual processing happening, or whether S2 is presented a little bit later in those stages. You're not going to start working on S2 on T2 until you're done with T1, right? It also suggests here that there's no real effective letter intensity on those short SOAs, and the idea here is that the argument is that when you have a short SOA, you have larger overlap between the two tasks, and the um, the low intensity letter would increase the amount of perceptual processing required. But the argument here is that, per the early selection theory, you're not even processing the letters here. So because you are not processing the letters, the fact that the letter intensity is weak doesn't really increase your perceptual demand at this stage, right? So once we're done with task one, then we're going to shift over to process task two, and we can dedicate more resources to it, right? So that's one possibility, right? So if early selection was correct, then that's exactly the pattern of data that we would see. We would find that you would have interference for both long and short SOAs, and that there would be no effective letter intensity specifically for the short SOAs. Now, what about our cognitive capacity model? This is late selection. So late selection, if you recall, says that we let everything in, comes into our internal cognitive processes and working memory, but there's a limited capacity for how much information we can hold in these internal processes. So now what's happening is that we are trying to handle T1 and T2 at the same time. Uh, but what we're going to predict here is that those short SOAs will have a much more dramatic interfering effect, and therefore really increase your reaction time to T2. By increase, I mean make it slower, right? Uh, and and why? Because there's greater task overlap. When those T1 and T2 kind of start really close to each other, they're overlapping each other even more, and therefore they're using up those limited resources. And and so because you've started to allocate resources to task one first, then T2 kind of has to take a back seat, but they're still in there fighting for resources a little bit. This is where we would expect the stronger effective letter intensity, because in the case here where you are trying to process both of these tasks at the same time and you're already using up resources for T1, now T2 becomes that much more difficult because of the low intensity letter, and it wants more resources, but maybe there's just not enough of those resources to go around. So we're really going to have a stronger kind of task depletion effect happening there. So when you combine short SOA with low intensity stimuli in task two, you would expect reaction times to just be really, really long. And that's the prediction of the late selection models here, that we're trying to do all this perceptual processing simultaneously. But neither one of these theories, whether early selection or late selection, has much to say about the response selection phase. They're really talking about the level of what's getting perceptually processed, right? And this is where we need to add some additional thinking here, right? Maybe it's not about the perceptual processing so much as it is about the response selection. So if we make this hypothesis that interference occurs during the response selection phase, then this would imply that we can simultaneously engage in the perceptual processing of both stimuli, but what has to wait is the choice to perform the response. So this theory would predict that The short SOA will produce interference because the tasks are overlapping each other quite a bit, and we're just going to have to wait till task one is done before I can perform, or I should say R1, right? So I have to R1 is the response associated with task one, and all I have to do is I can process the stimulus of the letter, right? But I just can't select a response until I've performed R1, right? So once I have figured out the appropriate response to task one, which is R1, then I can finally select and perform R2, right? But this would imply then that this is largely going to be more significant for the short SOA because the tasks have this much overlap, right? They're going to have a high amount of overlap. That's the same prediction, by the way, as the cognitive capacity model. So you might ask, how do we test between the capacity model and this bottleneck theory that I'm talking about? Well, the bottleneck theory makes the prediction that at these shorter SOAs, there will be no effect of letter intensity, right? There's a little typo there. It says no of effect. Sorry about that. No effect is what I'm trying to say here. Whereas the capacity model said a strong effect of letter intensity. Why? Because according to the capacity model, making the task two more difficult by manipulating letter intensity is going to use up those resources. But what the bottleneck theory is saying is that we're allowed to engage in perceptual processing at the same time. And where we have to wait is just at the response selection phase. So what that is going to suggest here is that while this response selection phase is waiting, that just gives us extra time to process the low intensity letter, right? So even though that's harder to process, we've got a little free time, right? So just like with my example that I was giving about the computer doing things in the background, that's exactly what the bottleneck theory is suggesting, is that at least at the level of perceptual processing, we can have that stuff running in the background, but it's at the level of the response selection stuff where we can only do things one at a time. So that's the idea, is that all of this perceptual stuff is getting processed. Some of those perceptual processes might take a little bit longer because of their level of difficulty, but since it's allowed to happen in the background, then it can be done, and it doesn't necessarily have a big effect on our performance. Uh, and then we just have to wait for the first response to be done, and then we can perform the second response. So this would imply then that it is possible for me to perceive and attend to multiple things at the same time, but I simply cannot do many things at the same time, with the emphasis on do, right? I cannot select and perform two responses at the same time. I've got to do one response, push the buttons for the tone, and then even though I've already kind of internally decided which button I got to, or what the stimulus is for the letters, I can't think about that response and then perform that response until I'm done with the first response, right? And so that's what the data shows, right? So when we think about what was the actual finding, which of these three is supported, my note at the bottom is that it supports this bottleneck theory. So it doesn't necessarily direct the early versus late selection theories as so much as it says that there's additional interference that occurs at the response selection phase. And that's, again, it's another kind of helpful thing to think about when it comes to cognitive control processes here. Okay, so as I said, I wanted to stop it here. And so I'm going to save the working memory content for the next video, and hopefully we should be able to finish this content then in just one more video. Okay.